Very good morning. I am sure you got the graphs for multivariate normal distribution. Today we will see the geometric interpretation which will further help you in understanding multivariate normal distribution. Today we discuss statistical distance, constant density contours, and then some examples. Hope you are enjoying the lectures. Let us see what is there for you today.
We will continue multivariate normal distribution. Today our discussion will be on two issues. One is statistical distance including constant density contours, constant density contours, and then we will see that how to determine that your data is multivariate normal. So, examination of data for multivariate normality. Okay. So, let us see statistical distance first. Suppose you consider two variable case x 1 and x 2. Now, this is, let it be, this is the origin with mu 1 and mu 2 in that sense. So, let us give this point name as O, and you want to know the distance from O to P. P is another point. What is x 1 1 from 1 and your x 2 1. So, that means this point is from variable point of view x 1 1 1 and x 2 1, or other way you can write that x 1 2 you can write that manner also. So, then the distance between these 2 points, that is O P, that all of us know that this is x 1 1 minus mu 1 square plus x 1 2 minus mu 2 square in the square root. This is a point with coordinate values. For x 1 this is x 1 1, for x 2 this is x 1 2, and this is the reference point O with mu 1 and mu 2 as coordinate. Then the distance is this distance is known as Euclidean distance. Euclidean distance. Now, let us see that we have several points. We have several points scattered on a bivariate plot x 1 and x 2 in such a manner that it basically resembles like this. The figure is like this, or you can increase this. Okay. Now, if you find out all points equidistant from this O, that is mu 1 and mu 2 coordinate, all points equidistant from O, that means the equal Euclidean distance, and if you join them you will get a circle. So, all points on this circle are equidistant. Okay. Now, we will go to the process level. For example, I told you in one of the classes that we have a manufacturing process and that process takes certain inputs and gives certain output. This output is measured in terms of its quality. Let there are two variables you are measuring here, x 1 and x 2 related to the output. It may be related to the process also. Okay. For the time being, let us concentrate on the output. Then if you make a plot of x 1 and x 2, you may get a figure like this. You may get a figure like this. Okay. Now, with little assumption, in the sense that as if the figure resembles an ellipse. Okay. Then I am keeping another observation on x 1 and x 2, which is here, closer to this mean point, let it be here. So, as we have assumed earlier also, this is our mu 1 and mu 2. This is one point, let this point is q, and let another point somewhere here, which is p. Correct. Now, if we go by Euclidean distance, OP, the distance between O, the origin, as well, and P, it will be greater than OQ from Euclidean distance point of view. Euclidean distance, what we say, that all points which are equal distance, that will make an ellipse, and this is the, suppose I want to get equivalent distance with respect to q, OQ, that is the distance, then you will be getting something like this, the circle. When you make this circle, see, definitely OQ, this distance is less than OP. Correct. Suppose you do not know the distance concept, we are not interested in terms of defining the scattered observation from distance point of view, getting me. Then which one is closer to O, P or Q? Suppose if you see the scatter plot, which one is closer to O, that mu? P. This P is closer to O. The reason is because the general mass, the behavior of the general mass is like this, like an ellipse, and point P belong to this general mass, whereas point Q does not belong to the general mass. So, from the process point of view, this is outlier, Q is outlier, whereas P belongs to the general mass, because our figure is like this, it is like this, your point is here and all values are like this. Instead, your Q point is here, Q and P. It simply indicates that if we go by Euclidean distance measure, we cannot capture this behavior. What is the problem here? The problem lies, see, the variability across x 1 and x 2 is not captured in this equation, and it is because of the variability along the two dimension, the difference in variability, you are getting this structure. So, we want to include variability into the equation. Now, let us see if we give weightage to each observation by its variability, what will happen. Suppose we will now first we will write this O p square in the general sense x 1 minus mu 1 square plus x 2 minus mu 2 square. X 1 and x 2 are two variables. This is your Euclidean distance. Euclidean distance, CLEDIAN distance. Instead of this, if I give weightage to the observations by its variability, I can write like this: x 1 minus mu 1 by sigma 1 square plus x 2 minus mu 2 by sigma 2 square. That means, the mean subtracted observation is weighted by 1 by sigma 1 as well as 1 by sigma 2 depending on the variable. So, this one if I write this is O p square, is it not an equation of ellipse? Definitely, but not this ellipse. It is equation of ellipse, but not this ellipse. Why? Here what happened? There are correlation. So, if we can change. So, this is an equation of ellipse and it represent two variables which are independent like this. So, if I say across x 1 variability high, x 2, then this one is our equation of ellipse, and if you take a point here, suppose this is your P, this one is O is mu 1 and mu 2, and P if say x 1 and x 2, then this O P, this distance is this one. This is the formula for this distance. And as this one is equation of ellipse, all points on this ellipse, the distance will be computed using this function. And what we say here? We say all points on the ellipse are equidistant. This is the all points on the ellipse are equidistant, definitely from O, from a reference point. If you take this ellipse, what will happen? Your O p square, you can write x 1 minus mu 1 by minus or plus, you write whatever may be, you write plus some constant will be coming here, let it be a 1 2 I am giving, x 1 minus mu 1 by sigma 1, x 2 minus mu 2 by sigma 2 plus x 2 minus mu 2 by sigma 2 square. This is the covariance part between the two variables. Okay. This is what is statistical distance. Okay. This is what either this elliptical distance, this is what is statistical distance. So, in essence that the statistical distance, one of the pioneers in developing this is P.C. Mahalanobis. Okay, he is Indian scientist. He is founder of ISI, Indian Statistical Institute. Okay. Now, look at the slide. In this slide, there are in the right hand side there are 4 figures. First, the leftmost one, top one, that one resembles circle. Second one, it basically depicts one ellipse. Third one is also ellipse. Fourth one is also ellipse. but the second and third one, the variability along x 2 is more in case of second one, and in case of third one the variability along x 1 is more, and in case of fourth one it is there are change in variability as well as there is correlation between the two variables. Okay. So, first one is random, in the sense we are saying that the two variables are independent. Second one also two variables are independent, third one also two variables are independent, only in fourth one variables are dependent. Now, you think that this is a bivariate case, you think from multivariate point of view. So, when number of variable will be more than 2, then it will be difficult to pictorially visualize, but the points are there. So, ellipse will become ellipsoid, ellipse to ellipsoid. Hyperellipsoid. Okay. So, can you tell me that what is the difference between this figure vis-a-vis this figure? So, if I say this is my quadrant 1, quadrant 2, quadrant 3, quadrant 4, quadrant 1 versus quadrant 3.
In quadrant
1 and quadrant 3,
quadrant 1 and
quadrant 3. This is quadrant 1, this is quadrant 3.
variability along x axis
Yes.
is more than is less than the variability
Along y axis or x 1 and x 2. We have given x 1 and x 2
and y are uncorrelated.
uncorrelated. Okay, first quadrant, second quadrant, third quadrant variables are not correlated. Now, what can you talk about the variability of x 1 and x 2 in the second quadrant? The circle is there. Variables are uncorrelated and variance same, along x 1 and x 2 variance is same. So, if x 1 x 2 variance is same, then it will ultimately resemble a circle. If there is difference in one of the axis, the length will be more, that will be the major axis, other one will be the minor axis. If there is correlation, ultimately the total ellipse will be shifted to other direction. Okay, this is very important concept. Later on in principal component analysis, we will again bring back to this figure. There we will see that if they are highly correlated, what is the need of measuring so many variables? Can we not measure a smaller number of variables? That we will discuss. Okay. I think if you look into this figure you have seen earlier also, and this equation also you have seen earlier. What is the exponent part of a multivariate normal bivariate normal density function? This is the exponent part, and we have also discussed that the exponent will resemble an ellipse. So, that is the distance. This is what is the statistical distance. Okay. What will be the distribution of this exponent part? Yes, it is chi-square. Why it is chi-square?
X minus mu by sigma, that square. So, that is basically the
Yes, x minus mu transpose, then sigma inverse x minus mu, that is the exponent part, and minus half is there, we are not considering that minus half. You see this x minus mu transpose and x minus mu, that is the square term of normal variable, and this capital sigma is the variance part, covariance part. So, what your capital sigma is population sigma, it is a constant value. So, the square of normal is your what is square of normal is z, and z follows chi-square, the linear combination of z follows chi-square distribution. So, this will follow chi-square distribution, that what we are saying, probability that this value will be less than equal to chi-square p some alpha value, this will be 1 minus alpha. Now, in this equation mu sigma sigma are population parameters and x is the random variable. And your chi-square distribution will be different types. The shape of the chi-square distribution can be like this, can be like this, can be like this, depending on the degrees of freedom. And you all know how to see chi-square distribution. Chi-square distribution, degrees of freedom is there one side, and other side the probability values. Then we will discuss contour, what is basically constant density contours. You see this figure carefully. This is bivariate density function. This is the mu, that is the bottom reference point, you just see that is coming through. If you just see the from the top, if you see what you will see, you will first see the point for this top point. Then if you come little distance lower and take a cross section, then you will be seeing this ellipse. If you come even little more, you will be getting the second ellipse. Like this, you will be getting different ellipse, and as we have already discussed that all points along this ellipse is equidistant. We have proved this one by statistical distance, they are equidistant. So, here what is happening, that's why the total data set, the total data which is represented by this MND, here it is basically bivariate normal distribution, and you are capturing now. Now, the more you want to include more number of observations, your ellipse will be bigger. What does it mean? What I am trying to say, suppose your case is like this, your case is like this, this is the case. Now, if you take this, you take like this is your cross section here, this is the cross section, then what is the portion you are considering? You are considering a smaller portion. If you take a cross section here, you are considering a bigger portion. So, as a result, what is happening? Your ellipse is becoming like this. So, I can say this may be 25% ellipse, this is maybe 50% ellipse, this one may be your 75% ellipse, this may be 95% ellipse. What does it signify? It signifies that 25% of observation will be on or within this ellipse, 50% will be within or on this ellipse, 75% will be on or within this ellipse, and 95% will be on the ellipse, and that is what is this one alpha. If you choose alpha equal to 0.05, then you are creating an ellipse in such a manner that this will be 95%, 0.95. That means, you are considering 95% observations to be within or on the ellipse, rest 5% will be in other out of this region. So, why we are saying this one is constant density contours? What is why we are saying this is constant density contours? What is contour?
So actually these are the footprints of constant density loci. If we take get a elliptical
elliptical region.
usually footprint.
This is the plan. That's why I said if you see the plan view from the top, you see in the floor itself the footprints will be generated, and equal distance points will be making one ellipse. Why constant density contour? What is the contour? A contour line of a function of two variable is a curve along which the function has a constant value. This is Wikipedia definition. So, our function is f x, f x 1 x 2, that is the function, and we are taking when we are making a cross section here, that means we are taking a constant distance, constant density, and suppose you are taking this 0.5 as the density, then along this that 0.5 we are making a cross section, and that cross section will bring certain ellipse here also. And as a result, we are saying that this is constant density. That means all the points on this ellipse, this is constant density, having constant density.
So one next in the definition,
Hmm.
when you have seen shown the Wikipedia definition.
Hmm.
So there is that a contour line of a function of two variable. A contour line of a function of two variable. But sir, contour should be generally for n number of functions.
Yes, yes, it can be. It is not that only two variable case. For example, we want to draw a contour on the world map for the cities having equal altitude. That means from the mean sea level, you will find out the city's distance, that altitude value. If you join a line, that is also contour, distance contour. Similarly, temperature contour, same manner. It just you think here what is happening, you think from a hill point of view, this is a hill. Now, from the floor of the hill, bottom of the hill, you are going up, and after certain height make a cross section. As this is the height, suppose this is my floor, this is the height. So, this is the density, you are making a cross section there. Need not be that it will be a two variable function of two variables, it can be function of many variables, and ultimately our case is multiple variables only. Here one example. Consider the data given in example 1. Obtain constant density contours for alpha equal to 0.05 and alpha equal to 0.01, and we have seen that the d square, this is x 1 minus 100 by square root of 10 square, this one we have given earlier. Considering this equal to chi square alpha. Now, when alpha equal to 0.05, then this will be chi square 0.05, variable is 2. So, degree of freedom is 2, and you have to see this value. What is this value? This value is 5.99. So, now this is the ellipse, this is the ellipse which is basically taken into consideration chi square 2.05 5.99, means we are this is the ellipse what is basically constant, all the points having equal density value. Now, how do you get this 5.99 value? This is what is the chi square distribution, and when your degrees of freedom for that distribution is 2 and our value is 5.99 c, this is 0.05 5.99 this value. If it is 0.10, then your value will be 4.61. So, ellipse will be little smaller. Okay. Any question from your side?
Suppose in case of two-dimensional data, we have an inclined ellipse as you shown. Here x and y are co-related. Now, what is the degree of freedom? Is it 1 or 2? I think it is.
No, that degrees of freedom case is purely dependent on the number of variables considered. Whether they are correlated or not correlated, it is immaterial.
But sir, at the time of correlation, the distribution should be should the distribution will change?
No, the ultimate exponent value will be different because distribution will not change.
You know that chi-square distribution means z square basically, summation of z square. But now that separate terms will also come if there is a value of correlation.
No, that will not be. That is not correct. If there are p variables, then our case is e to the exponent is this one e to the power minus half transpose this one. You are talking about this part. This part. Whether there is, because this is covariance matrix sigma, so definitely there is correlation or covariance. We are considering this correlation component or covariance component. This here basically if we say this, we are not going to statistics, it is a population domain. So, this expression is chi-square distributed.
So number of variable involves equal to
Degrees of freedom always. Okay. So, that means what we are saying that x minus mu transpose this x minus mu, it is chi-square p. Now, I think your question is, suppose if you go for some transformation of the variable, then your number of variable will reduce because of correlation. Suppose if the data is correlated, when you go for principal component analysis like analysis, what will happen? Your number of dimension will reduce.
Actually, I thought the rank of the covariance matrix, that is the number of independent variable, should be the degrees of freedom.
No, here it is not like this. Here the covariance component is well accounted for the derivation part. Okay.